Introduction. In this unit, we shall discuss the properties of some of our other senses, especially hearing, the implications that these properties have for user interface design, how senses, other than vision, may be used in human-computer interaction. Look at the mechanisms by which sensory inputs are processed by the human cognitive system. How we are able to pay attention to certain sensory stimuli and mental activities. What implications this has for interface design. How human memory works. Look at the relevance this has for interface designers. Sound in the interface. The vast majority of computer-based user interfaces that we encounter rely almost totally on the visual medium. However, another medium that is frequently used in interface design is sound. Let us now look at the properties of sound and hearing. A number of properties of the audio medium are pertinent to the use of sound in the interface. Sounds can vary in a number of dimensions: pitch or frequency, timbre or musical tone, and intensity or loudness. Not all sounds or variations of sound are audible to humans. The ear is capable of hearing frequencies ranging from about 20 Hz up to about 15 kHz, and differences of around 1.5 Hz can be discerned, though this is less accurate at high frequencies. The capability of computer sound output devices to produce variations along each of the dimensions of pitch, timbre, and intensity means that sound output is potentially a rich and sophisticated medium for conveying information to users. We shall now look at inherent properties that constrain the way humans process and make sense of the sounds they hear. Understanding these constraints will be crucial to the successful use of sound in interactive systems. In contrast to vision, sound is a volatile medium in the sense that sounds do not persist in the same way that visual images do. Or, to put it another way, the visual field can be regarded as a parallel array of information elements, each of which may remain constant or may vary over time. Sound, on the other hand, can be seen as a single element described by its pitch, timbre, and intensity that may vary over time, and the rate at which it varies, or carries information, or is perceived, is not under the control of the listener. Its potential as a means of conveying information, and the amount and type of information that can be carried, is therefore rather different from that of the visual channel. Consequently, the visual channel can be regarded as frequently having a much faster access time. For example, a large amount of information may be made simultaneously available in the visual channel, whereas presenting the information in the audio channel may take longer, as the information must be serialized. A further implication of this is that an audio information stream may place greater demands on the user's memory while listening. To part of a message, the user must remember what has gone before. When reading a visual display, the parts previously read remain visible. Another relevant property of the audio medium is the fact that, unlike vision, hearing is non-directional, while binaural hearing does grant us a limited ability to determine the direction of a sound source. There is no sense in which we can listen in a particular direction. Similarly, while we can very easily control our visual sense, for example, by looking in a particular direction, it is much harder to be selective about what one listens to. It is well known that people are rather good at noticing changes in sound, such as the onset or cessation of a noise or tone. However, we are rather less good at extracting information from a stream that remains relatively constant. In fact, if a background sound remains relatively constant over a period of time, we will tend to become less aware of it, and eventually will filter it completely and cease to notice it at all. A further property of sound and hearing that designers should be aware of is that we are relatively poor at separating out a single sound or sequence of sounds from a background of similar sounds. Why sound plays a very important part. The majority of information we receive about the world comes to us through our visual sense. Sound plays a central role in communicating with others through speech and other sounds, receiving information and entertainment through radio broadcasts, musical performances, and so on, and allowing us to be aware of events, some of which may be outside our visual field, police sirens, ringing telephones, etc. Sounds that are apparently in the background often give us vital clues about the status of ongoing processes, for example, the sound made by a car engine as we are driving, the noise made by machinery in a factory. Despite the apparent limitations described above, sound is a remarkably important channel for conveying information. Next we will look at some of the ways sound is used in current user interfaces and how it could be used in the future, and will identify some guidelines that can help designers to make the use of sound more successful. Sound is currently used in many computer interfaces and other interactive devices, sometimes as an important source of information and, at other times, simply as a means of making the interface seem more impressive. Sound can be used for both input and output functions in an interface, and the kinds of sounds that are used include abstract tones and bleeps, naturally occurring sounds, music, and, of course, speech. The audio channel is, for most of us, a rich and important source of information in interactions with other people or with the environment. However, sound has played a more limited role in human-computer interaction than in other aspects of life. Part of the reason for this may be that it is not always clear what kinds of functions sound is appropriate for and how to make effective use of sounds to support those functions. Let us now look on the audio alerts. What is the purpose of such a bleep, and what can the user infer from it? Clearly, the sound indicates to the user that something has happened, but it is typically left up to the user to determine, by other means, the nature of the event, an erroneous input, or a system-generated warning, or simply the arrival of email. Its source, one of several applications, the operating system, networking software, and what should be done about it. The following rather extreme example highlights the kind of problematic situation that can arise. The point is that, although alarms and alerts can be successful for indicating that some event has occurred, they often carry little useful information about the nature or location of the event, or what should in response. And if several notable events occur together, then providing an auditory indication of each is simply going to confuse users. The world of power stations and control rooms may seem very far removed from everyday design, but the same issues are relevant in the interfaces of desktop systems and the design of web pages. Sound output, therefore, must be used with care. Sometimes it is appropriate to indicate a change of status or a particular event with a sound, but we must be aware that beeps and similar alerting sounds often provide the user with too little information about either the nature of the event or what action will need to be taken as a result. Used with care, however, sound can enhance an interface and provide users with an important source of information. Providing more information. The simplest and most basic sounds are simple bleeps that indicate an event or change of state. However, other possibilities exist. An idea that several researchers have experimented with is to add sounds to many of the familiar features of existing visual user interfaces. So, in addition to the visual cue provided by an icon, an auditory cue would be provided as a further memory aid. The sounds used in some of these experiments were natural ones, chosen to match the kind of interface objects with which they are associated. For example, folders on a desktop might have the sound of paper crumpling. Presumably because, in the real world, we put paper into folders, and dropping an item in the wastebasket might produce a sound of breaking, because things sometimes break when we throw them in the bin. While this might seem an attractive way of providing the user with additional feedback and extra ways of remembering how the interface works, it has some problems. One is that the same sound might mean different things to different people, so the sounds are not as natural as they first seem. Another problem is that, while auditory equivalents may readily be found for some interface elements, there are a great many computer-based objects and operations for which no real-world audio counterpart exists. One researcher in this area, Stephen Brewster, has taken up the idea of augmenting existing visually based interfaces with sounds to assist the user, but has used abstract sounds rather than naturally occurring ones. These sounds, known as earcons, icons for the ear, are made up of short musical phrases that vary in the sequence of notes, overall pitch, tempo, and so on. Earcons have been added to icons, menu items, and so on of conventional computer interfaces. Speech output. In communicating with other people, we most commonly make use of speech, and our interactions with computers can be similarly speech-based. Speech synthesis has been possible for quite some time, but it is only relatively recently that using synthetic speech has become a reality in everyday interfaces. However, speech is becoming increasingly popular as an addition to more conventional user interfaces. Sound input. Sound can also be used as an input device. Almost always, in human-computer interaction, this means using voice recognition, a relatively new technology that is beginning to achieve the level of performance needed to be effective. One often hears a view, presumably inspired by science fiction movies, that if only we could just speak to our computers, then all our usability problems would be solved. Indeed, we would no longer need user interfaces. It must be emphasized, though, that voice recognition is yet another kind of user interface technology, and just like the mouse and keyboard, it therefore is appropriate for some things and not for others, and using voice input has just as much, or perhaps more, potential to create usability problems as any other technology. A number of products exist that allow standard desktop computer systems to take speech as input. For instance, recent versions of Apple's macOS operating systems allow the user to speak standard commands such as solve, print, open, and so on, which the computer interprets and executes. Typically, though, users spend only a small part of their time entering commands into a computer, and much more time entering and editing the content of their documents, so a facility for speaking commands is only of limited use. A number of products are available that allow users to speak text to the computer, which is then used as the input for word processors and other software. While voice input might be a nice addition to existing desktop computer systems, it is likely to play a much more central role in interactions where using familiar visual output and mouse and keyboard input is difficult or infeasible. One such situation that we have mentioned before is the provision of services that will be accessed by telephone using only the auditory channel. Several products exist that allow designers interactive, telephone-based services to incorporate voice recognition technology. This allows users to provide information, commands, and so on. For example, the Vocalis Group markets a range of products and has made demonstrations available over the telephone. We will now look at some suggestions and guidelines for when and where sound might most successfully be employed in their user interface for both the output and input channels. Sound output. Audio output may be the appropriate channel to use for giving immediate feedback that an action has taken place, buttons on ATMs, telephones, etc. that beep or click as they are pressed. Presenting different kinds of information to that made available using the visual channel, for example, non-static information such as alerts. Augmenting visual interfaces by providing additional information and cues, for example, earcons. Supporting users for whom the visual interfaces are not an option, for example, those with visual impairments. Supporting users whose visual senses are already heavily used for other parts of their task, for example, aircraft pilots. In interfaces where visual information cannot be presented, for example, mobile or handheld devices with small or no screens. Audio output may not be particularly good for constantly changing status information. Use in shared offices or workplaces where privacy is important, or where the output of many users' computers would lead to confusion or disturbance. Noisy environments where sound may be difficult to hear, for example, the user interface of machinery on a building site. Quiet environments where sounds could cause distraction, for example, a library or recording studio. Voice input. Sound can also be used as an input device. Almost always, this means using voice recognition, a relatively new technology that is beginning to achieve the level of performance needed to be effective. Voice input may be appropriate for users who are unable to use more familiar input devices like the mouse or keyboard, for example, those with severe motor impairments. Users who are busy doing other things, for example, an aircraft pilot whose visual channel is occupied monitoring the approaching runway during landing. Interactions that may be cumbersome using the other interaction devices that are available, for example, menus used in mobile phone services. Small and predetermined range of spoken commands. Voice input may not be particularly good for noisy environments. Use by many different users with different voices and accents. Wide range of words or a specialized technical vocabulary. Note that some commercially available voice recognition systems have versions adapted to technical specialisms such as medicine or law. Things that are not easily verbalized, for example, diagrams. Other senses, other devices. So far, we have looked at how sound and vision can form parts of the interface between user and computer. We now ask the question of whether some of our other senses and physical abilities can be used in order to facilitate human-machine communication. The use of other senses is usually proposed for one of two reasons. The first is to replace a sensory channel that is more often employed in user interfaces. This is typically so as to make a system accessible to users with sensory impairments. For instance, if touch can be used to do some or all of the work of vision, then a system will be more accessible to blind users. The second reason is to add to or augment the experience created by senses already used. For example, if the website about cookery were able to allow users to smell the results of cooking, the effect might be a richer and more enjoyable experience for the user. Touch. In everyday life, we use touch and related senses that give us information about temperature, texture, pressure, body position, and orientation, and so on, as yet another way of gaining information and feedback about objects and events around us, especially those with which we are interacting most directly. Currently, little use is made by interface designers of users' sense of touch. However, a number of experimental prototypes and products meeting specialized requirements serve as excellent examples of what is possible and what may become more significant for interface design in the future. Several devices have been designed that allow the computer to produce output in a form that can be sensed by touch and related senses. Such devices seem to be most successful in providing output that is tactile, that is amenable to the sense of touch, especially by having distinctive texture or shape, and providing force feedback where the user experiences the computer output as a force on their body. In some cases, these devices are intimately connected to the input devices through which the user issues commands to the computer and are therefore capable of providing instant and very direct feedback to the user. Tactile output. Output devices exist that convert the output of the compute into tactile form. For example, the text normally displayed on a computer screen can be rendered in a tactile language, such as Braille, making it available to users with vision impairments. For example, for a product known as Braille and Speak that allows blind or partially sighted users to take notes using a specialized personal organizer. Notes can be read back via either a synthesis voice or a refreshable Braille cell that turns text into tactile form. Tactile output devices of this type essentially use touch as an alternative output medium. Other devices rely on an observation about the way most human interaction with the physical world takes place. The separation between input and output that is so clear-cut in many conventional computer interfaces is not so sharp in other contexts. As we take an action in the real world, such as taking hold of a cup and lifting it up, we get immediate feedback about the texture, temperature, and weight of the cup through the sensation of pressure in our muscles, joints, and fingers. Thus, the actions we take and the feedback we get as a result are very closely connected. A simple but effective way of combining input and output for user interfaces has been to allow a pointing device, such as a mouse or joystick, to provide physical feedback by making it resist the user's actions in a context-sensitive way, and provide tactile feedback as the mouse pointer is moved over screen objects. For example, the mouse is a mouse-like device that gives various kinds of physical feedback. If the user is dragging an object, the mouse will feel heavier than normal, and the user will be given tactile cues as the pointer moves over different kinds of screen object. For instance, moving across the edge of a window could produce a click sensation. Such force feedback mice are a relatively simple way of combining user input and feedback, but more sophisticated products exist. For example, the Phantom allows the user to move a pen, like stylus, through space in order to interact with the computer using gestures. Feedback is provided by mechanisms attached to the stylus that make it easier or harder to move or simulate the effects of different objects and textures that it comes into contact with. A similar input/output technique that has been developed for use with virtual reality systems involves the use of a data glove which senses the position, orientation, and movement of the user's hand, allowing gestures to be used as inputs and objects in a virtual reality system to be grasped. Several products exist that add force, pressure, or vibration feedback to a data glove, allowing the user to feel virtual objects they touch or grasp. For instance, Virtual Presence Limited markets a number of products in this area